So running a little bit behind, which is all according to plan. So I want to make sure that we take time to talk about these inner planets as much as possible because we have less and less knowledge about the bodies as we move further away from the sun, which kind of makes sense. We're going to have explored the things closest to us first. And so we spent a good deal of time talking about the moon last time, and I have a few more things that I want to talk about the moon, in particular with regards to our plans for the thing and how that's shaping up. But I really hope to make it through Mercury today, because Mercury is a very interesting body that looks a lot like the moon, but in some sense is only superficially similar to the moon. There's a lot more going on beneath the surface, and it's also a really interesting opportunity, particularly with Mercury and Venus, to talk a little bit about the mythology again, because Mercury and Venus seem to be at the heart of so many different ancient cosmologies. They're very unique, and we're going to talk about this in more depth later, but many of the ancient cultures thought of them as two different, they would treat Mercury as being actually two different stars, and the same with Venus, and that's because sometimes they appear in the morning and sometimes they appear in the evening. And their ability for the ancients, they saw this transformation between these two different, they thought of them as deities, obviously, and this transformation was reflective of the fundamental human predicament, which is life and death. And so we're going to talk about life and death a bit. We talked about life already, but the flip side of that, of course, is death, and the ancients struggled with this, and I think that I really think it's the fundamental human catastrophe is that as soon as we're born, we learn that we have to die, and this is something very unique to human beings amongst all the animals, that we have this conception of this future that awaits us, which of course is the key to our ability to make our lives better, but it's also something that we have to wrestle with. And so it seems to have been at the center of all of the ancient mythology, cosmology, proto-religions, is how do we deal with this death business? And of course, the answer to that seems to be something akin to rebirth, or let's say just birth in general. So the patterns that play out in the sky with Mercury and Venus were used by nearly every culture in antiquity, from the Mesoamerica to the Sumerians to the Far East. Everybody used these apparitions in the sky to tell the story of death and rebirth. And so there's a really rich mythological history there that I hope to tap into. There's also some really cool details about these planets that start to slot into our puzzle of the story, the physical story of our solar system, because in some sense, these two bodies, Mercury and Venus, are very similar to our proximal bodies, right? The one under our feet, which is in some sense compositionally and in terms of its size, it's very similar to Venus, what we're standing on. And the moon is very similar in size and in some sense in composition to Mercury. So we have these parallel worlds that we can in some sense compare and contrast and hopefully learn something about the strange behavior of our own planet, because obviously we have a really unique situation going on here and it's not entirely clear why that is. Of course, this magnetic field that we are privileged to plays a huge part in that, but there's some strange things going on because Venus doesn't have a magnetic field, and neither does our moon. But Mercury does, which is really strange because it looks a lot like the moon. It smells a lot like the moon. It essentially is very similar to the moon, but it has this magnetic field. So what's going on? And I think that we're on the verge of coming to some really interesting conclusions about the mechanism that generates that magnetic field under our feet. And I gave you a very simplistic picture of it before, but I think we'll uncover some cutting-edge details about that process as we work our way through Mercury and Venus. So maybe we'll get into Venus a little bit today, but hopefully we'll at least make it through Mercury. I want to quickly, though, review a bit about last week so we make sure we don't forget anything. Can somebody tell me something that they remember about our quest for understanding exobiology, particularly the motivation and who cares? Yeah, Shane.
I mean, we're really trying to find a planet that can also inhabit us as humans.
Yeah.
In case the Earth fails.
I think that's what it's all about, folks. We really are working in this extraordinarily long project, which I think, assuming humans can survive these political instabilities and so forth into the next 1,000 years or so, I think that this project will be viewed in retrospect. All of our space exploration will be viewed in some sense as part of the project to find a new home for ourselves. And so the story that we're telling about the moon and why I'm spending so much time on it is because in some sense it is the rehearsal stage for that project of branching out and finding another home. Does anybody remember any details about how we go about looking for another home exactly? What's that preliminary project look like? Yeah.
I remember something about how we basically take a pie shape, a small pie shape out of a long section of the galaxy and search for different colors.
Yeah, that's a reasonable way of looking at it. I mean, first we look for shadows, right?
Okay, shadows.
Yeah.
Right, yeah.
So what Dusty's saying is we just scope out a narrow column of interstellar space, and we look for these little shadows appearing across the stars. And that seems to be like the best screening method that we have. And you mentioned colors, and that's important too, because I think ultimately, and there is some preliminary data regarding this, is that we can see how the atmospheres, the gases in those atmospheres react to the light that's passing through them, and we can get some idea of the molecular composition. Now, does anybody remember what sort of molecules we're looking for? I kind of went light speed through this, so does anybody remember anything about that? Yeah, go ahead, Shane.
I mean, there's water, carbon dioxide.
Yeah, water's huge, right? That seems to be the most important piece of the puzzle because as far as I can tell, and as far as anybody can tell that's been in any way convincing to me, water seems to be absolutely the first piece in the puzzle of life. And we talked a little bit about how people imagine maybe silicone-based life forms are possible and stuff. I'm increasingly skeptical of this. A lot of folks are worried about this whole AI takeover business that's happening right now. But as far as I can tell, there's the fundamental feature of life is that it's generative. It has the ability not only to make more of itself, which you could kind of imagine robots doing, but it has the ability to imagine and sort of pursue goals and have this, to embrace the philosophical term, it has this will, right? It has goal-oriented behavior. And it's not clear that anything in the computer world has that. They set up these really interesting, have you guys seen these conversations where they try to pair two AIs in a conversation together, and it just quickly devolves into just complete, utter lunacy very quickly, right? They don't really have the ability to be generative in that sense. And so, anyways, it's not clear to me that that's going to happen. I think that we may engineer something approximating an artificial life form, but I think that it will start with water, and it will look a lot like building a cell from the ground up, something like that. So life requires water. That's a big one. We want to watch out for things that could be deadly to us too, right? And we can look for some of those, carbon monoxide, amongst other things that might rule out the world as being potentially habitable to us. The magnetic character is probably something we can look at too increasingly. I recently sat down with this wonderful astromagneticist, actually, who's looking at the role of magnetic formation, magnetic fields in the formation of galaxies. And so that data is just becoming online. It's very difficult to see magnetism when you look far away. The best you can look at is how magnetism affects atoms that are scattering light and how it polarizes that light, how it sort of lines it up or doesn't line it up. And so we're really in our infancy of being able to look at magnetism. But obviously, that seems to be the absolutely amazing and unique thing about this rocky world, is that we have a really strong magnetic field. Mercury, like I said, has a little bit of one, but it's super, super weak compared to ours. All right. And then in terms of the moon exploration, I'm going to round out the discussion of this today because it seems like, we're investing money back into this now. Private companies are investing money back into this. And the holy grail of moon exploration is going to be tapping into the water sources on the moon. So that's where I want to turn to right now. Does anybody have any thoughts or questions about the initial exploration of the moon and sort of the projects that we have going on right now? No? All right. So I'm going to launch into that a little bit, and we'll try to round out our discussion of the moon, which will point us into our exploration of Mercury, because very recently we've sent an orbiter out there to Mercury, and it's on its way. I believe it did its first real sort of flyby of Mercury in 21, and we're expected to go into orbit in 25, so we'll have a lot more information then. Okay, here's the thing. We need water in order to make rocket fuel. That's essentially at the heart of things. It's also a really important solvent. It's a universal solvent we talked about for life. Well, it's also a universal solvent for industrial processes. And so how we get to that water is really interesting. Now, the thought is that actually that rock that the moon is, well, the crust of the moon is principally comprised of it has a great deal of water inside of it. And so from some of these lunar samples that came back, they calculated that it had sort of sopped up this water at concentrations of 10 to 1,000 parts per million, which doesn't seem like a lot. But the hope is that there's actually, in some sense, great reservoirs of this down at the polar regions. And so a big part of our project there is to not only set up a permanent base, but to bring some sort of rovers that are capable of exploring deep down into the southern latitudes. There was an Indian mission which sent an impactor to the lunar surface back in 2008. And they actually went to the moon's north pole and discovered something like 600 million metric tons of water ice present in the craters there, which is promising. And so I think this is behind some of the gold rush to the moon, especially with the private companies and stuff. And you can imagine that, I think we touched on this last time, but there's a great deal of industry available once you have the ability to start doing work on Mars, and water is at the heart of that. Let's see, what do I want to say about this? NASA had another orbiter that mapped the water content of the surface. This was in 2012. They, in particular, checked out this one crater called the Shackleton crater and found that ice makes up something like 22% of the material on the floor of that crater, which is pretty remarkable. All right. There's also helium. Now, helium is really an interesting atom. The helium essentially accrues as a result of solar wind. And the problem is that we're actually running out of helium here on Earth. A lot of people don't realize this. The problem is that our magnetic field does a great job of screening out solar wind, which means we don't get a lot of helium to replenish the helium that we presumably started with at some point here. The moon, not having a magnetic field, accumulates helium in abundance. And so helium is actually, it's an interesting element. You've probably seen the helium balloons and things like this. Like, it's a nice curiosity. But in terms of where fusion research is headed, we talked a bit about the promise of fusion and the pitfalls of the approaches, but helium seems to be an important substrate in any future fusion reactors that we build. And so that's an increasingly important element that we're going to want to find on the moon as well. It is important in some technologies on Earth, like MRI machines and things like that. It's used as a coolant for a lot of these high-power magnet systems. So helium. We'll dig that up there too. Now, what makes it, we talked about the benefits of doing industry on the moon and so forth. What are the downfalls of that? What's the problems, actually? It seems like the biggest problem, well, first of all, it's really cold, and there's huge swings in temperature. It can go from, depending on the radiation that it's receiving, well, let's say what time of day it is on the moon, the temperatures can swing from something like minus 170 degrees Celsius all the way to 116 degrees Celsius. That's a really rough environment. So you're talking about really having to shelter yourself and build some pretty serious fortresses in order to not get hurt. The other big problem is radiation exposure. And this is a huge problem for space exploration in general. Like, the human body does not put up with radiation, right? It's very, and I'm talking about really high, short wavelength radiation, the kind of stuff with really fast impulses that are going to rip your DNA apart. And that's not an entirely easy solution set to imagine how we deal with that. There are some shielding mechanisms, but all of this adds to weight. It gets very expensive, gets very heavy when you're trying to, we use lead in the laboratory to shield ourselves against radiation. Perhaps maybe you guys go to the dentist and they give you x-rays, right, which is a form of radiation. And they put that big lead blanket across you. Well, lead is a very densely packed material. It absorbs radiation quite well, but you can imagine that you wouldn't really want to coat you wouldn't want to send a huge brick of lead atop a rocket into space. It just becomes very economically difficult. And so that radiation business is a huge problem. I had a friend who was working at a private space company, and they were investigating all sorts of interesting solutions about this in terms of actually recycling the waste from the astronauts in the outer shell of the space capsule, because human excrement does a great job of absorbing radiation as well, it's very interesting, the different solution sets that they're imagining. I actually think like the bioengineering of these solutions is going to be a huge factor in all of these in terms of coming up with something lightweight that's sustainable. And I mean living absorbent materials, right? Maybe things like fungi and mushrooms might play a role in that, which is quite interesting. Something that could be generated in situ, right? Once you've actually got those spacecraft in orbit. Another problem, low gravity. Does it matter? It seems to, actually. So when folks are out on the International Space Station, they have, in some sense, the ability to, they can set up these different exercise stations where they basically tie themselves to, say, a treadmill or something like that. And this is able to, in some sense, combat the problems with the lack of gravity. But there's more to it, right? I mean, your bones require you to be, in order to have strong, dense bones, they need to be under pressure at all times, right? And it's not totally clear what other systems in the body require this. How does the immune system react to low gravity? How does the circulatory system? Are we going to have problems with heart disease and cancer as a result of this because the immune and the circulatory systems aren't functioning properly? That's a huge concern. And there's different strategies for this. Once something is in orbit, you can use the equivalence between inertia and gravity to simulate gravity, right? You can spin something sort of like a centrifuge. You can spin a space station potentially and generate something approximating gravity through that pseudo force of centrifugal motion, right? You can spin people against the walls, basically. Sort of like one of those crazy amusement park rides. But that's more difficult to imagine how you would pull that off on the surface of the moon. So it might be that people can only spend a little bit of time on the moon, right? It might be that you can't really have a permanent residence on the place because it's just too hazardous to our health. And then the final factor is that there's this really, really fine and abrasive dust that's coating the whole surface of the moon. And it's really, really gnarly to machinery. I don't know if any of you have had experience with trying to use power tools and so forth when in dusty conditions. Particularly, it's really bad in the desert for people. But I've experienced a few times just out here during the dryness of the summer. You get dust inside of gears and so forth. It can really damage metal tools, and so that's a huge problem too. So it sticks to everything. It was a huge problem for the early Apollo missions in terms of threatening their equipment and the functionality of their spacecraft. So it's not going to be an easy situation. There's going to be a lot of experimentation, and I think there's going to be a lot of ups and downs for moving forward with this. There's also the politics of the situation, which is quite interesting. So who does the moon belong to? That's a great question, right? Humans have chopped the surface of the Earth up into all of these little countries, right? Where presumably the people who know the place best can autonomously govern their own circumstances. People made this treaty we talked about with Antarctica, for instance, that nobody would really own it. People could use it for scientific bases. And they tried to set something up similar with the moon back in the 70s, I believe. It was called the Treaty on Principles Governing the Activities of States in the Exploration and Use of Outer Space. The problem is, if you look at the countries that signed that treaty, they're not the ones that are sending things out to the moon, okay? So everybody who actually has the power to go to the moon doesn't really care much for the treaty, and it's a bit of a free-for-all. So I don't know what's going to go on with that, but that seems like it could pose a serious threat to the smooth and efficient colonization of the moon, because the last thing you want is armed conflicts, hundreds of thousands of kilometers away from, well, not that far, but thousands of kilometers away from us. So this is a problem, and I'm not sure that anybody sees a solution in sight for that. All right, let's talk a little bit more about the actual moon before we move on to Mercury, like the actual physical surface of it and its history. In particular, the most popular theory, which is pretty much brand new in the last 10 years, as far as I can tell, is this idea that the moon was formed during this giant impact, which is a very interesting and attractive theory. In some sense, it's more appealing than the idea that they formed simultaneously from the same group of stuff, because they're very different in composition and so forth. But I think that this theory also suffers from, in the sense that the moon doesn't have an atmosphere and it doesn't have a biosphere. This is a little bit troubling for me too, because the moon doesn't have anything approximating an atmosphere, and I'm sure that there's rationalizations for this, but it's strange to me that a body could have impacted the Earth, and somehow the Earth got all of the good stuff, and the moon just ended up being this rocky mess instead. This is very, very perplexing, and I think there's some other problems too, which we'll look at. In particular, the cratering of the moon with regard to the dating regimes is proving more and more problematic. I actually saw a really interesting article, should have put it up here, this weekend, which was that they're examining a lot of these. So we periodically get bombarded with material from Mars. And the problem is they started dating some of these meteors from Mars, and they found them to be only a couple hundred million years old, which is perplexing because Mars is supposed to be much older than that, obviously. Furthermore, it's not thought that much has happened on Mars in the last couple hundred million years to result in any new material being formed. And so the conclusion of the authors was something like, we have some serious problems with the way that we're doing this radiological dating, because we don't have the ability to rule out the sort of amalgamation of that material, right? Remember, this is something I've been talking about since the beginning. These dating methods that we've used to make these declarative statements like the Earth is this many billions of years old and so forth, they're really indistinguishable from saying that the Earth, the material that we're dating, was cooked into a molten blob that many years ago as well. And so the timelines are very, at least in my mind, the timelines are a little bit up for grabs still. And there's some interesting problems with that because, of course, the other way that we date things is by the accumulation of impact craters. So let's talk about that a little bit. First of all, we have to understand there's basically two main crustal features on the moon. There's these lowlands, which are called maria, and there's these highlands, which are, not exactly mountainous, but they're of a slightly different composition. The highlands are a bit less dense than the maria. The idea is that as the moon cooled and solidified, this is sort of like some sort of slag floating on top of a smelted metal or something like that. The highlands are also extremely cratered compared to the maria. And so the idea initially, and I guess to some extent persisting, is that the maria were formed later. There's something like volcanic flow, right, that covered up a lot of the craters that were there before. And we'll dig into that a little bit more in a second. It's interesting, too, that the highland, the quote-unquote mountainous regions, they don't have, like, the cliffs and jaggeds, they don't have Mount Everesty looking things that we would have on Earth. And the thought behind that is that, well, we have wind and water and erosion that forms a lot of these steep surfaces here on our own planet. And also tectonic activity, right? There's something going on with the constant remodeling of our crust. And, whether that's the sliding around of these plates or in some sense the remodeling through other seismic processes, we have the ability to generate these really sharp peaks and so forth that we just don't see on the moon. And I think that makes a lot of sense. So here's some of those craters. You can see there's a lot more in the white areas, right? These are the highlands versus the maria. Originally, I think I mentioned this last time, but most people originally thought that these craters, especially the first people to observe the moon through the early telescopes, and for a couple hundred years after that, they were convinced that these were actually volcanoes, which is totally, in some sense, reasonable, especially if you start treating the maria as volcanic plains, right? But that didn't seem to hold after a while, in particular because if you examine the way that volcanoes form, they're usually at the top of these mountains and so forth, and we don't really see that on the moon. There are some volcanic mounds throughout the solar system. We see them quite clearly now, especially on Mars. There's a couple of enormous volcanoes, which we'll talk about when we get to Mars. But essentially, the idea is that the processes that form volcanoes and those that form impact craters are very different. Now, bear in mind, part of the reason they thought this is because they they hardly ever saw anything smash into the moon, right? They didn't see these craters being formed. And so it was logical, in some sense, to assume that they must have formed through other means. One of the big tells, though, that they are, in fact, impact craters has to do with these streams of ejecta, right? You see these, what do they call these things? Crater rays. Call these crater rays. And these are something like the spallated ejecta after an impact. And so that was kind of a dead giveaway. But again, the history of these craterings is a bit perplexing. I believe I pulled this picture out of your textbook, which is really interesting. So let me break this down for you. One of the earlier ways, before we'd actually gone to the moon, of estimating the age of these bodies, and Mercury, other planets to some extent too, was that if you knew how often these craters formed, you could trace that backwards and get an age. And so, we have been able to date some of this rock of the maria, and we visited this place in the 70s. We were able to date some of the rock between the maria and the highlands, and what's really perplexing is that they don't really have much of an age difference between the two, okay? And so this is very troubling because if we think about the number of craters that had formed in the maria since they were formed, which was supposed to be very close to the formation of the moon, some 3.8 billion years ago. The problem is there's 10 times more craters in the highlands than on the Maria. So if we actually date it based on that, we come up with an age for the moon that's something like 38 billion years old, right? And this is, of course, not only older than the standard issued age for the solar system, it's also something like 3 or 4 times the age of the universe, according to the cosmologists. And so the only solution that people could come up with to rectify this was that at some point in the deep past, there was just this extraordinary period of bombardment where it was just hammered with asteroids very intensely. Which is an interesting proposal. However, we don't really see that same thing on Earth, which is, a bit troubling. So I don't know what's going on with that, and I don't know that this is obviously some sort of a paradox that we need to wrestle with. Could the solution be that everything's a lot older than we think it is? Well, there's a good deal of precedent for that in the past. I don't know if I've made this plain to you yet, but as early as, let's say, 200 years ago, most geologists thought the Earth was somewhere on the order of 6,000 years old, okay? So that wasn't that long ago, and honestly, these timelines, if you look at the history of the timelines of everything in astrophysics, they keep expanding and expanding and expanding. Even this, we're not really doing the cosmology stuff this semester, but the timeline for the universe itself seems to be receding as well, and that's a huge controversial point in cosmology and astrophysics right now concerning these anomalous observations from the early universe now that we have a more powerful telescope to see very, very far back in time. So, these stories are constantly evolving, and I think that's what's really exciting about this class with respect to being an intro science class for you guys, is because you can really see how we have to change our minds periodically and how painful it is to do that, especially in the modern age when we build up, we've built hundreds of years of papers and literature. There's Nobel Prizes given for ideas that almost certainly have to be supplanted at some point. And it's not entirely clear how you go about doing that. How do you come up with an idea for which there have been celebrations and prizes for, right? It's in some sense an equally malevolent force to the church enforcing the geocentric vision of the universe, right? You have a lot of pride behind these assertions and these theories. And they're very difficult to rewrite as a result of that. I'm not totally sure what the solution to that is, except to maintain some humility that science has to be a process of incrementally understanding the world better. And we can't fall in love with our theories too much. We have to accept them as just the best way of explaining things that we have at any given point in time. So this is a really interesting paradox. It's something for you guys to contemplate. The history of this thing doesn't totally jive with itself and with the context of the other worlds that we see. The moon is if you look at it, it looks extraordinarily old. It really does, especially compared to something like the Earth. Now, could that be because the Earth is just very active and it's constantly remodeling its surface? Absolutely. It could be. But we do have some evidence of impact craters going very, very far back on the Earth. There's some in the billions of years region, and they're still few and far between compared to something like the lunar highlands, right? It's not this completely pockmarked thing. So why is that? Why are they so different if they are supposed to have come from the exact same, they essentially come from this stay-in impact between two protoplanets. It's very strange and perplexing. All right. I think that I'm ready to talk about Mercury. Does anybody have any more moon questions? Yeah? All right. So here they are. The moon and Mercury. Very similar looking. Now, Mercury doesn't have those nice maria in the same way. It's almost entirely looks a lot like the lunar highlands, which is interesting. Mercury also does have more of these cliff-like things, and we'll talk about the theory for why it has more jagged mountainous regions. It's a bit different, but Mercury is much closer to the sun, and so a lot of the differences that we attribute to Mercury come down to the fact that its internal fluids, right, its magmatic innards are being yanked around quite a bit by the sun, as opposed to the side. Earth is quite a small body compared to the sun, and so the forces that it puts onto the moon are much less as it gets yanked around. Mercury also has a really eccentric orbit, so it's not this nice circle, right? It's very elongated, which means that it sometimes comes in very close to the sun and then gets peeled away very quickly, and so there's more sloshing going on, which is in some sense thought to account for the presence of its magnetic field. Let's see here. All right, this is kind of interesting. All right, so a bit about the history of looking at Mercury. So, like I said at the beginning here, Mercury and Venus are both interior to us. And this means that when we look at them in the sky, we have the opportunity to see them at either one of these positions with respect to the sun, right? They can either appear in the east or they can appear in the west, depending on the place that they occupy in the moment that they're at in their orbit. So this has the appearance of essentially presenting an evening star or a morning star to our ancestors, well, to us too, but it was very, very important to our ancestors. Here's another way of looking at that. This is the eastern elongation. And so this was not insignificant, and I think that we should unpack that a little bit. So the word Mercury comes down to a Roman deity, Mercury, who is a very interesting character, but it actually in some sense stems further back to the Greeks, and probably before the Greeks, to maybe before them were the Mycenaeans, before them were the Minoans. To some extent, the Phoenicians were overlapping with these peoples. It's very hard to get a grip on that exactly. But Hermes in Greece, or the Romans, Mercury, was an interesting character who was something who had an evolving role throughout history. Started off with this really strong underworld associations, this strong Chthonian character. Later became a messenger, a shepherd, and so forth. The god of boundaries, let's say, even with respect to sexual reproduction, this is a very sexual entity because, in some sense, breaching the boundaries from it has very sexual overtones to it. And what's up with this? You see it over and over again, and we're going to get into it more when we talk about Venus. But this idea of let's imagine what this looks like to people who don't have any kind of conception of the solar system as we know it today. This entity is in the sky, descends down below the horizon, disappears for some amount of time, and then comes up again on the other side of the day. And so there's this natural narrative which builds about this descent into the underworld. And of course, the underworld is associated with death because, well, what happens when someone dies, right? I mean, from tens of thousands of years ago, we have evidence. One of the first signs of anything approximating behaviorally modern humans is that they buried their dead in the ground, right? And so, I mean, they're finding this even with pre-human hominids. The Neanderthals, Homo naledi also, I think, is one of the earliest burial sites that they found in this cave. So people were dragging their dead into the ground. There's this very ancient association with the ground and the world below us being that which is occupied by the dead. And I think the fact that the earliest associations that we have with human behavior have to do with burial rites concerns how important of a crisis it is for humans. This death business is such a crisis. And it doesn't seem to be with other animals, which is really interesting. There are like some glimmers of that, say there's some signs that elephants, for instance, some of these more cognitively enlightened animals, whales as well to some extent, have the ability to mourn their dead to some extent. And in some sense, that correlates with their ability to have some sense of self-consciousness, right? And I think that the emergence of self-consciousness is really the fundamental defining human feature. And it traces really nicely with this idea of death, because once you realize that you have a separate entity that is distinct from everybody else, and that you have that autonomy, then you start to realize that what's happening to other people might happen to you. And when you see someone die, you start thinking, oh no, that might happen to me as well. And this is extremely troubling, but it's also at the heart of what makes us humans, because once you have the ability to recognize that, now you have the ability to invent time for the first time. In the first moment, as soon as you have this ability to see stages of humans as stages of yourself, the old people that are dying, that will be you someday. Now you have the ability to wield time. And time is an incredible invention because it allows us to investigate futures that might or might not occur, right? In some sense, just like Alfred North Whitehead said, ideas are the way that we die without dying, right? We can kill off these bad ideas instead of killing ourselves off. We can imagine going this way or that way in say, an exploration of a landscape. One's going to be more dangerous, and so we're just going to not do that one. We're going to try something else. That seems to be the fundamental defining ability of humans. I've really started playing with this idea that what makes humans human is that we're time machines in this sense. We go deep into the past and see what we screwed up, how we could do it better in the future, and we imagine all these potential futures that we may or may not want to live out. But with that comes the knowledge that this will all end for everyone here, and for everyone that we know and love is going to someday not be here. And I don't know that is a trauma that anyone ever entirely recovers from, which is interesting. I think that in some sense, it's at the heart of all of our decision making, and it's at the heart of a lot of our suffering here on Earth. And so what I think people were trying to do with these mythologies, let's say proto-religions, and I think that this is at the heart of every religion on Earth today, is in some sense that they help people navigate this journey from birth to death. And I think that was a fundamental fixation for the humans in telling stories, as they did with the stars in the sky, or what we now call planets. They thought they were stars. Of course, Venus is not a very bright body. Venus is quite bright. Mercury is not very bright. But Venus also does this transition, as the ancients would have thought, into the underworld. It can be an evening or morning star. And Venus is actually the most bright object in the sky after the sun and the moon. And so it makes sense that this would play a very prominent role in the storytelling that would happen there. And of course, if your goal is to navigate this most central fracture in our human existence, then it makes a great storytelling apparatus. So these ones mattered a lot to the ancient people, and I think they mattered a lot because they reflected something that mattered a lot to us in our daily lives. Really, really important. And I'm not sure that anybody has great solution sets for what to make of death, except for the fact that in each one of these traditions, and as is reflected in the sky, there's a rebirth element. And so you see this in almost every religion, there being some sort of rebirth element, right? And from like a purely biological standpoint, if we just forget about religion for a moment, there is something magnificent about the fact that humans are constantly being created. This is actually a really remarkable feature that, if you talk to people who have kids, maybe some of you have kids, the moment that people have kids is generally the moment that they stop being absolutely, devastated by the idea of death. Because in some sense, that is our path to immortality. That is the way that we continue. If you think about the cells in your body, which are really just one cell, an embryo that happened to divide up into a bunch of compartments, that cell came from another living being that lived before you, your parents, right? And before them, that cell of their body that became all compartmentalized into all these other cells came from another one, all the way back, as far as we can possibly imagine. all the way back to the tiniest single-celled organisms, right? In some sense, that cell has persisted for billions of years up to this moment. And so there is this immortality available in the principles of birth that in some sense alleviates the suffering associated with dying, because it can very tangibly be realized by having children, that things of you go on, you actually continue on in the world. So this seems to have been the fundamental revelation of the ancient peoples, and it seems to be at the heart of all their mythology. And in some sense, Mercury plays very much into that, and it gets more developed, of course, as the different civilizations proceed. And, Mercury takes on this role of being a sort of messenger, right? It leads you through this passage into the underworld and out. There's more to that story, too, and we'll get into it when we get to Venus, because I think that the journey into the underworld has a lot of different dimensions to it. Of course, it starts off with this really, really primal catastrophe of death, but there's more to it than that in terms of being reborn, especially in your daily lives, right? In some sense, every time something bad happens to you, right? Let's say you fail a midterm exam, or your significant other breaks up with you, or you lose a family member that's close to you, anything that happens to you, in some sense, you're thrown into that underworld, right? And the ancients realized this progressively and were able to mirror this experience onto their mythologies. And so we'll talk about that with respect to Venus, because in some sense, the only way to get over these tragedies is to sort of be reborn and to remake yourself differently in a way that's in some sense stronger and able to carry that. And so the stories of the journeys to the underworld all capture that self-renewal story. And we'll talk about that more with Venus. So everybody all around the world was obsessed with Venus into antiquity. China, Mercury, they called Mercury the hour star, ancient China. In Hindu mythology, they used the name Buddha, which is interesting. In the Norwegian, the Norse gods, it was associated with Odin. This is all very interesting, by the way, because everybody associated it in terms of the week with Wednesday, which is interesting. Wednesday is, of course, comes in the English language, comes from Woden's Day, which is, of course, regarding the supreme god Odin. But it's also, if you Latinize it into, let's say, Spanish or something, you get miércoles, which is Mercury. And this is really interesting that people came up with this same association over and over again in different reaches of the world. What more do I want to say about that? Okay, even the Mayans, we don't have time to get too much into this, but the Mayans represented Mercury as this owl, and it served as a messenger into the underworld as well. And the Mayans have a very rich underworld story that they also developed with Venus. And if we are sticking completely with the mainstream archaeological narratives, there should be no interaction between the people in Mesoamerica and the people, say, in Sumeria or Greece. And they came up with almost identical mythologies about this journey to the underworld for their deities associated with Venus and with Mercury. That's pretty remarkable. So either there's something so fundamentally important about this story that everybody comes up with the same idea when they look at these apparitions in the sky, or they actually have, some common roots. These stories are essentially so old that they predate the civilizations themselves. These stories may have been stories that people, let's say, proto-humans were conveying to one another at such a distant reach in history that they found their way into these cultures that were separated by continents, by oceans from one another. All right. Now, every once in a while, Mercury passes in front of the sun with respect to us. The last time this happened was 2019. It's not going to happen again for more than a decade. And so there's been a few splashes of people mentioning that maybe they saw this in antiquity, which is interesting. There's a hint of it in the 12th century from the Islamic scholarship, which most Western scholars wrote off as them observing sunspots, but the date of the recording in those annals was commensurate with the date of an expected transit of Mercury. So people may have been seeing this happen. Venus also does these transits periodically, but they're very few and far in between because in some sense, well, especially with Venus, Venus's orbital plane is not aligned to the ecliptic very well. It's inclined quite a bit, and so these transits are few and far between from our perspective. Mercury is very, very tiny. Can you guys even see Mercury on this picture here? Maybe people at the back can't even see it. It's very, very, very hard to see. Now you can imagine people in the 12th century staring at the sun, how they would have even managed to have picked something like that out. It's hard to imagine. I've actually seen sunspots with my naked eye a few times, and it's only possible. I saw one this past summer, and it was only because it was one of those really smoky days, and the sun. Sometimes you get a really beautiful picture of this pink sun, and right around sunset, not like a few hours before sunset, there was this beautiful view of it in my backyard, and I could see. I actually thought it was a transiting planet at first. I was like, oh wow, and I went and looked, and no chance of that. But yeah, it turned out to be a sunspot. So I think that under the right conditions, you could actually view some of these things, and it's reasonable to assume that our ancestors were able to do that to some extent. All right, let's talk about the internal landscape of Mercury a bit. Mercury is weird, like I said. It has a magnetic field, but compositionally it doesn't appear to be all that different than the moon, which is a bit remarkable. There's also something else which is very strange about Mercury. It's very, very dense. It's so dense that with respect to the size of the Earth, the only way to make sense of it is that its solid inner core is enormous, occupying something like 57% of its volume, whereas our solid inner core is something like 17% of our volume. So the thought is that it has this huge solid component. And we talked about, when we were talking about magnetism in the Earth's under our feet, we talked about the importance of the solid metal in retaining the stability of the magnetic field. Now, the best theories that people have come up with are quite interesting in and of themselves because they involve an evolution of this planet. The idea was that at some point it was much bigger, and there's reason we'll talk about why they think that. But in some sense, it's necessary in order to explain why it has such an enormous core. And if it does have this enormous core, maybe the magnetism in some sense is a remnant of when it had a much bigger molten area, the mantle area, that was swirling around in order to induce that magnetism in the core itself. So in some sense, we might be left with something of a permanent magnet that's a remnant of that. Now, it's huge too, by the way. Mercury's core is something like the same size as our moon. This is really remarkable in terms of the relationship between the size of the mantle and the core. We don't see that anywhere else in the solar system that I'm aware of. Actually, I have a picture of that. So here's kind of a comparison of the different rocky bodies. Venus and Earth, we'll talk about them in a second. They're really, really similar, which is troubling because they behave, or their outer surfaces are very dissimilar. Mars, Mercury, but obviously Mercury has much more of an internal landscape. Now what's really strange, though, is that Mercury doesn't seem to have any sort of geologic activity on the surface. In other words, it doesn't have any volcanism. It doesn't appear to have anything approximating fissures or plate tectonics or anything like that, which is really, really strange. That's what makes this cohesive story almost impossible to tell, right? Because every story that we want to tell that relates the similarities of these planets in their formation process, they diverge really quickly in these really painful ways. This will become abundantly clear when we start looking at Venus versus Earth, because the stories that we use to tell about how our own, let's say, tectonics unfold with these convection conveyor belts, or the story of our magnetic field, all of those processes should be occurring on Venus as well, right? There's plenty of geologic activity on Venus. It seems to have plenty of volcanism and magma and all of this. Ruptures in its crust, but yet it doesn't have the same swirling, there's no reason why it shouldn't have all the convection necessary for plate tectonics or for the production of a magnetic field, and yet it does not. And so why is that? It's not totally clear inside of the bounds of the stories that we tell about these planets. Likewise, Mercury is troubling for similar reasons because it has all of this internal activity, right? I mean, it has an appreciable magnetic field, so something must be sloshing around inside of it. And I mentioned that the best reason that we have for that is because it has this eccentric orbit, so it's getting more sloshing than, say, the moon would get with respect to the Earth. But with all this sloshing, why doesn't it have volcanism? Why doesn't it have surface cracks or plates moving around, right? And I don't know the answer to that, except for I think that, actually, I mean, the best answer that I can think of for any of this is that the dating regime that we have is insubstantial. It's not enough. These things, I think that the only way to explain all of these things is that these bodies are much, much, much older than we think they are. It's one possibility anyways, but as long as we have these boundary conditions on the age of the universe being a mere 14 billion years old, I don't think we'll be able to entertain any of those possibilities. Okay. Let's see what else here. Oh, this is kind of interesting. So another reason why it seems like Mercury is extremely old, and the moon for that matter. You know, one thing you can imagine is that, you know, let's say under the Thean hypothesis for the creation of the moon, if you have two planets that mash into each other, well, a natural consequence of that is that their rotational vectors, what can we call these? They're spin vectors. The angle at which they rotate is going to be knocked off kilter a little bit, right? That's a natural thing to assume. And in fact, the Earth does seem to have we're angled at over 20 degrees, right? This is why we have seasons. This is because we're not perfectly in line with the plane of the ecliptic. But Mercury is almost perfect, right? It's almost perfectly in line with the ecliptic, and so is the moon. That's really, really interesting, because to me that says that they've had a lot of time to stabilize over the years, right? But we still are kind of working on this 17th century hypothesis that goes all the way back to Kant and Laplace, that these things all formed exactly where they started, right? And there might have been some motion and some wandering and some evolution, but more or less it's a uniformitarian perspective on the construction of the solar system. There's no room for planets coming from outside of the solar system and joining in the melee. There's no room for any of that. And I think that strains the mind to imagine. And I guess I'm not trying to tell you that that's the way it was. I just want you to understand that these stories are absolutely evolving, and I expect to see them change quite a bit in the future. So this is kind of interesting. You know, you can see Mercury, almost no inclination of its rotational spin axis. Mars is quite similar to the Earth. Pluto is just off on in its own universe over there, right? Almost completely inverted. Uranus is also extraordinarily inverted. We'll talk about that later. And so I think that these are also more clues that we can add into our story of the solar system. And I guess what I hope that each of you will be able to do by the end of this course is to start to imagine your own stories for this for the solar system, that there's probably more to it than what you're going to read in the textbook, because what we have in the textbook is something like a 300-year-old story that's crumbling quickly. And so I don't know the answer to the story of the solar system to give away the punchline at the end of this course, but I do know that the one that we've been telling for 300 years seems to be, in some sense, terribly inadequate to explain a lot of these features. So that's exciting. I think it's exciting anyways. I don't mean to pull the rug out from anybody. All right. So there's Mercury's eccentricity, you can see. Something really beautiful. Anybody a musician out there, by the way? Yeah? 1, 2, 3-ish, 4. Nice. Me too. So what's really cool about Mercury, and we see this again in some other parts of the solar system, I'll keep bringing it up, is that Mercury is tidally locked to the sun, right? So it's basically facing the sun, sort of like a moon, which is really interesting. Our moon is also tidally locked to the face of our planet. But what it does is it's tidally locked in this 3-2 spin orbit resonance. So what that means is relative to everybody else, all the stars in the background, let's say, Mercury rotates on its axis exactly 3 times for every 2 revolutions that it makes around the sun. That resonance, right, that adds stability. Resonance always stabilizes the system. That means it's getting these periodic pulls and pushes at the exact same moment that it needs in order to continue moving in the same way. It's very, very comfortable, low energy conformation. But the 3-2 resonance is the exact same vibration resonance that you would expect from a perfect fifth in music. And the perfect fifth is an extraordinarily important resonance in music because you can actually construct every key on the piano by just going up a perfect fifth over and over again. So if you just draw out a perfect fifth, say from C to G, then do it again, then do it again, then do it again, then do it again. Eventually, you'll find your way constructing every single one of the tones in our modern scale. And if you keep going, you'll end up in microtone worlds, which some cultures have embraced more than others. But the perfect fifth seems to be the absolute basis for music in our Western conception. So this is a really cosmologically significant resonance that appears over and over again. And yeah, I just think it's pretty cool that we see it there in Mercury. All right. Now, Mercury is a real nightmare to go and visit because during daytime, the surface temperature goes up to something like 430 degrees Celsius. After sunset, the temperature plummets to minus 170. So that's probably not going to be a very fun place to hang out. That's something like a 600-degree swing in temperatures in the Celsius. The outside is pretty homogeneous too, and so the thought is that it's the standard narrative that you're going to find is that the outside was at some point in its early formation this big magmatic ocean. Of course, that's indiscernible from whether it just melted at some point in the very recent past. Well, recent being billions of years ago. This is what we're looking at right here is a scan from the Mercury probe called Messenger, and these colors essentially, as far as I can tell, represent the different compositional readouts from the materials on the surface. I don't know enough about that. There are these cracks, though. Can you guys see there's this little mountain range here? It looks like a line. The idea here, as far as the best that people can reason, is that this involves something like the Mercury as it cooled after its formation, that it shrunk and these little wrinkles appeared, which is an interesting, it's an interesting idea. I don't know, but there are definitely these folds in it, and we don't see those on the moon. So presumably the moon would have also been undergoing such a cooling phase like this as well, but we don't see these folds. So those are a bit of a mystery. All right. Now, this is our latest space probe, which is on its way to check out Mercury. They launched this thing in 2018. It's called Bepi-Colombo. And it's going to have a couple of different, it's going to release a magnetometer in an elliptical orbit around it. And then it's going to fire an actual probe to land on the surface so that we'll actually get some information about the material there in depth. This thing is not supposed to arrive until 2025. The magnetometer, I guess, will be able to also study different wavelengths of light, infrared, ultraviolet, X-ray, and gamma ray information from the surface. So that's where we're at. We don't know a lot about this thing yet. It's a very strange, anomalous body. Looks like the moon, but it tastes nothing like the moon kind of thing. So, very interesting one. Looks like I'll have some time to get into Venus. Does anybody have any questions about Mercury? All right. Now, again, Venus makes a wonderful it makes a wonderful addition to our potential stories of this solar system. Like I said, because it's so similar to Earth, and yet it's so very, very different, right? And you know, there's a number of ways in which things can be similar but different. So if we think about biological evolution on Earth, you think about, well, there's basically 2 ways that you get a similar form for biology, right? So, for instance, you can have, let's think of something. How about a whale, which has flippers and a tail and swims in the ocean? But you also have fish, which have flippers and tails and swim in the ocean. But it turns out that they actually evolved from very different lineages, right? The whales are, of course, mammals, which is very strange. So at some point, they developed on land first and found their way back into the waters. At least their ancestors at some point did. Whereas fish have always been in the water. And they developed ways of breathing in the water, right? Extracting oxygen from the water itself. So they're very different paths to a very similar phenotype. In other words, a very similar form. And so I think that that's a really reasonable way to start thinking about the planets too. You know, if two planets look the same, there's basically two ways that can happen. Either they formed exactly under the same conditions in the same place, or they adapted to those conditions because they evolved through completely different environments and then found themselves under similar circumstances. And it's not clear how we separate those things out, but the mysteries that appear about their differences can maybe inform that. For instance, if we were studying whales and fish, we might initially be like, okay, well, obviously these creatures came from the ocean. But then if we looked closer, we would start to understand that the whales were breathing using lungs, which is very similar to the land animals. And we might say, well, that kind of throws a wrench in our idea that they both evolved here in the water. And so the same thing is the logic that we need to apply to these planets when we're trying to construct these stories for the solar system in our own minds. So here we go. These are two different views of Venus. This is actually what Venus really looks like if you were to have a really good telescope and check it out. It's covered in this really, really thick gaseous atmosphere. These clouds reflect something like 70% of the sunlight that falls upon them. And they're really, really nasty stuff, too. They're not the kind of clouds that you might find on Earth. They're full of nasty, really toxic, acidic gases, sulfuric acids and stuff. And if any of you have had a chance to play around in a chemistry lab, sulfuric acid is about as nasty as it gets. It's probably well, I'm not a chemist, so I won't say anything more. It's really bad stuff. So you wouldn't want to be breathing that. In general, Venus is a really, really, really painful place to try to hang out at. It rotates extremely slowly, right? Its year, in the time it takes to go around the sun, is actually much faster than its day. That's how slow it rotates. It's also a really weird one because it rotates the wrong direction with respect to all the other planets. This is very, very bizarre. So the picture that we have over here was filled in by an orbiter mission that was sent a long time ago called the Pioneer Venus Orbiter. And what they did here is they actually do something sort of like radar of the surface to get beneath those clouds. And that's how they're able to image the actual surface features. And in some sense, the surface of it is sort of chopped up and very active looking like the Earth, right? It has a lot of cracks in it. It has a lot of this magmatic business. We're on our way back to it with another project that's being prepared, which probably won't be there until the 2030s. I had a chance to sit down with one of the NASA scientists who was designing that mission. And a lot of the assumptions that are made in terms of the geologic activity are not really confirmed because we haven't really been able to get down there. I believe the only time we've landed on the surface was this Soviet project. I don't have the numbers here, but I think that lander that the Soviets sent, it survived less than a half an hour on the surface. Right, it's really, really gnarly. The pressures are extremely great, right? You can imagine that atmosphere weighs a ton. And so it's just a real awful combination. It's like being a submarine in the worst possible, acidic, hot environment imaginable. It's not a good place for human exploration. And so the one that they're developing right now, I can't remember, but it's expected to be able to persist for a number of days, I believe. And that will be really interesting because I think we'll have the chance to actually, it's also going to be taking pictures and measurements as it descends down to the floor. So it should be able to get some nice pictures of these volcanoes if they are in fact active. We sort of assume that they are, but we don't have any first-hand pictures of that. So that's going to be really, really cool. Look forward to that in like 10 years. The surface pressures from all that atmosphere is like 100 times that we feel on the Earth today. It's really, really significant. So At that pressure, it's very, very thick. There's almost a buoyancy to it. It's almost feeling like a liquid at that point. It's so dense, right? And it's interesting to think that in the evolution of a number of these planets, maybe they had thick atmospheres, right? This is something that doesn't get a lot of play in the story of our solar systems, and I think we talked about this with respect to some of these kind of fringe theories about the early Earth with respect to having a thick atmosphere. You know, perhaps that's a reasonable explanation for how the dinosaurs were able to sustain themselves without crushing their own legs and so forth. Maybe the atmosphere was a lot thicker in those days and added some upward buoyancy. Of course, that's not a theory that most scientists are willing to entertain, but there's no reason that it couldn't have been the case. So it's really, really, really nasty, really, really thick atmosphere, really hot, really acidic. Not a fun place to go to. Now, Venus played, I want to just remind you guys that Venus played an important role in the establishment of the heliocentric model back during Galileo's time. In fact, Galileo was able to use his telescope to observe these phases of Venus, right, which kind of sealed the deal, because you can't really see these phases with the naked eye. You can definitely see Venus. Venus is, like I said, it's essentially what you would think of as the brightest star in the sky. If you ever want to know what that bright star is, it's probably Venus. It's obviously not a star by conventional definitions, but it is a very, very bright body. But it's very difficult to pick out the phases with the naked eye. And there's a few people, there's some, you can watch some YouTube videos and so forth where people claim to be able to pick out the phases of Venus with the eye. And so, you know, there's this way of making like a small aperture with your hand and being able to exclude the light so you can see a bit finer. And there's ways, and there's people who testify to being able to see the phases. And it's possible that in the history, the deep history of observing the sky, that some folks were able to pick that out. But apparently not enough of them to argue en masse for a heliocentric worldview. However, right, it seems like maybe places in the East, and particularly India, seems to have at least understood that the Earth was some sort of ball of dirt, and that there was something approximating the solar system configuration. And it's not clear how they knew that exactly. But if they were able to see the phases of Venus, that might have been a good giveaway. So, yeah, that was a crazy paradigm shift. And Galileo really, you know, the Copernican idea was on the table. It was not accepted. But when Galileo was able to actually turn his telescope towards this actual phenomenon of the phases, that's when the paradigm changed. And it was devastating, of course, to the pride of the authorities at the time. And this is just something that happens, right? These are things that we have to go through. We're going to go through more of these. They're going to be very painful for our authority structures. You know, I would say most people on the street really just want to believe that somebody knows what's going on in the sky, right? I mean, to this day, I think most people just want to believe that, you know, whether it's NASA or whether you're alive in the 1600s and it's the church, somebody has a bead on what's happening up there. And so when we have to rewrite that, it's a very, very painful, you know, pan-psychologically painful moment, I think, for humanity. And so we have to look forward to more of that in the future. That'll be fun. Okay, this is a picture. I wanted to show you why Venus's transit is so difficult to see. The last transits occurred in 2004 and 2012, but the previous pair was in the 1800s. And so, unfortunately, I don't believe we'll get to see one of these in our lifetimes ever again, which is a bit tragic. But it's cool to look at. There's actually some modern pictures of it. That's, of course, because of this tilted inclination, right? A lot of times when we pass Venus, it's just outside of the plane of the sun, so we're just not able to see that transit. But it's pretty cool. It's easier to see when it did happen in the early 2000s. It was much easier to see than, say, a Mercury transit, which happens more often because, of course, Mercury's period is much shorter. So there it is. You can actually probably see that one. But you're only going to see it in pictures, unfortunately. You'll never actually see that one. You know, Mercury traces out, from a geocentric point of view, it traces out this really, really beautiful, what do they call this, pentagrammatic pattern. You know, and this was actually a huge arguing point for the geocentrists at the time. They said, you know, this pattern must have been designed by it must have been designed, right? You couldn't actually stumble on this. And therefore, because the pattern is so beautiful, it must be the reality of the situation. The Earth must be at the center of the solar system because these patterns are just so beautiful. And that's really interesting. It seems kind of like a crazy argument from a scientific standpoint, but the funny thing is that you still hear this exact same argument at the forefront of like fundamental particle physics and so forth. You know, most physicists are absolutely obsessed with the ideas of unification and simplifying and beautifying their math, right? You'll often talk about, I think there's a number of quotes from famous physicists where they talk about, they know they have a really groundbreaking theory when it's elegant and beautiful, and they ascribe these things to it. But I think that can be a really dangerous mindset because in reality, nature is actually, it can be quite crusty and complex and not simple and beautiful like this. And so this is not how the solar system works, despite how beautiful it looks. By the way, the Earth-Venus resonance, so this relationship between our orbits with respect to one another is a ratio of 8 to 15, which isn't, we don't find that interval in our modern scale, but you do find it in some cultures actually. It's called a neutral sixth, so it's somewhere between a minor and major sixth for you musicians out there. I think you hear some of these subtones more in Eastern music, and yeah, there's a couple of cool Turkish instruments that do these microtones as well. They'll just have like a guitar with like hundreds of frets on it, as opposed to the normal pattern that we see. So more music in the sky, just not the music we're used to. All right. Look at these patterns. They're just absolutely gorgeous, but they're not real, is the problem. Okay, so, well, they're real, but they're not telling us about the physical motion of the bodies, which is very confusing. I mean, I think that's the really, really troubling part of relativism in general, is that relativism can tell you something that looks the way that it looks, and it's absolutely accurate and precise and so forth, but it doesn't necessarily inform you anything about the physical relationship between the bodies at the end of the day. You don't necessarily have a true model of what's happening. So Venus does this thing which is kind of cool. It actually drags a big swath of asteroids around with it, and we see this again with Jupiter. And I think that I'll wind down by explaining to you this idea of Lagrange points, because it's going to come up over and over again. It's really important for our space exploration. But there's this really interesting thing which appears in gravitational, let's say, gravitational dynamics. And this is a better illustration of it in some sense. I generally loathe these gravitational well ideas, but I think that this helps illustrate it in a very nice way. If you think about the gravitational presence having to do with being scaled by mass with particular bodies, what happens is when you set up an orbit of another body that has also a gravitational presence, what you do is you essentially you develop these two neutral points in the lead and the lag of that orbit, which are stable orbital points. That is, the influence of gravity is, however you look at it, it's minimized at that point, such that you can actually place chunks of material there and they won't fall out of orbit. They won't start their own orbit. They'll just stay in those points. And those points are called Lagrange points. In particular, we label them L4 and L5. And so these L4 and L5 points are just full of little tiny asteroids that just follow Venus around in its orbit. Jupiter has some of these too. It has a huge conglomerate. They call them the Trojans. These huge masses of asteroids that lag and lead Jupiter's orbit. And these things, the reason I think they're important to pay attention to is you'll often find when you read, say, a pop science headline, you'll hear about the L2 point and the L1 point because that's where we stick satellites often, right? If we want to have something, let's say, that doesn't involve the sun, we want to block out the sun's light, we can put satellites in these really stable gravitational points, generally at L2, which is kind of on the opposite side of the Earth from the sun. And so these L2 points are very gravitationally resonant points that we can utilize for studying the cosmos, because we can just plunk our satellites there and they'll stay there indefinitely. So they're really, really useful. And we learned about these by watching the different pockets of asteroids around Jupiter and around Venus. So anyways, let's put a pin in it. We'll continue with more of Venus next time, and eventually we'll make it to Mars. And yeah, have a good week, guys.